मैडम मेरे को वॉल्यूम दे दो 9 ICSE का वॉल्यूम दे दो। Still some time. 2 minutes, so we can. Tell me, where did we stop last class? So जब मैं था लाइट शुरू किया, जब मैं आया था तो लाइट शुरू किया था। अच्छा, तो क्या क्या किया लाइट में? Did you bother to check? सर आता नहीं है, इंस्टेंटली नहीं आता, 2-3 वीक्स बाद आता। इसमें नहीं आता। नहीं, वीडियो ऑलमोस्ट लास्ट टाइम तो फिजिक्स का जब मैंने देखा 3 वीक बाद आया। हमने यहाँ पे कौन से टॉपिक खत्म कर लिए वो बताओ मेरे को। हमारा हीट हो गया है कि ज्यादा बाकी है बस। तुम तो रेगुलर हो ही नहीं तो पता नहीं आ रहा बाकी है। कौन बताएगा मेरे को? सर मेजरमेंट्स हो गया, मेजरमेंट डायमेंशंस हो गया, लॉज ऑफ मोशन हो गया, चैप्टर 4 और 5 हो गया, हीट हो गया। मेरे ख्याल से हीट तो हो गया है हमारा। हीट हमने पहले किया था या हीट अभी चालू है? If see, you have to know or you have to update your notes. How do I know where were we in the last lecture? Hmm? So you have to. Okay, first check. Last class was holiday here, right? Last Thursday was holiday. So when did our last class happen? So it must have happened in September. Okay, so it must have happened on 25th September. Let's check. So हो गया ना 3 हफ्ता होना चाहिए. Yes. Okay, now we have so it is 9 science, right? It comes in science, right? Sir, sound क्या था फिर 9th science university. Sound start किया था? फर्स्ट पेज तक कर दिया। अच्छा, अभी याद आ गया तुमको? ठीक है, यूनिवर्सल ट्यूटोरियल्स। एडमिट कैसे मिलेगा? वो लिंक रहता है,
मिलता है
मैंने सर्च किया तो अलग है पेशेंट्स
ट्यूटोरियल. Okay. See, this is what it is. Okay. So now three years ago, yeah, 9th ICSE science. It's 9th ICSE science. Okay. So we'll go here. आज क्या डेट है? 9th October. Okay. So Vashi, Sanpada, Copper Girne. Right. This is the Copper Girne playlist. And here we'll see. So chemistry, physics, 25th. This was the last class. Okay. So we will know what we were doing. Yes. Propagation of sound waves. So we had done these two questions, and then where did we stop in the end? So we discussed already what is sound, and we also discussed how sound is produced. Okay. And then we are discussing oscillations. Okay, it was just a basic introduction. So did you attend this class? Okay. So last class you were absent. I was also absent because last class there was no class. It was holiday. Okay. He was also absent. You were all absent. Okay. So it was Dashera, right?
Dashera.
Yeah. All right. Let's begin our class for today. So now have you understood how to look for your class? 9th ICSE Science. It will take you to this YouTube channel. Then you can particular, and all the subjects are arranged in specific playlists on that channel. And then just search your timetable. Okay. On that day, you will find the class. And uploading does not take that much time. It happens almost instantaneously. The moment class stops here, within an hour or two, it happens. All right, let's start. Okay, so are we getting this view? Why not other view?
ऊपर है.
हाँ तो नीचे क्या नहीं आ रहा है? स्विच कैमरा. ठीक है ना, स्विच कैमरा कर दिया मैंने. या फिर 1 सेकंड. ओनली वन कैमरा इज वर्किंग. नहीं नहीं, दोनों ही चल रहे हैं ना. ये वाला है और ये फ्रंट वाला है. So 1. वो तो है ऑलरेडी. ठीक है. So I'll just say switch camera so that you see the board. Okay. Now, so in the last class we talked about what is sound. So you also present for this.
Yes.
So what is sound? It is a form of energy, okay, that produces sensation of hearing in our ears or brain ears. Okay. So then how sound is produced? Sound is produced by What is produced? It is produced by
Vibrating.
vibrating objects. Okay. It is produced by vibrating objects. So let's discuss some examples of sound produced by vibrating objects. Can you give me any example? Most basic example of sound? What is the most basic example of sound on a daily basis? Not speaking.
Speaking.
Most basic is speaking, right? So what is vibrating here?
Vocal cord.
Vocal cord. Okay. So the example is vibrations or vibrating vocal cords. Okay. Produces sound when we speak. So what causes the vocal cord to vibrate? The air coming out of lungs. You know, when we speak, air comes out. Vibrating vocal cord produces sound when we speak. Second, strings of musical instrument. So when you pluck the cord of the guitar or sitar, so vibrating string of musical instrument. Okay. Or the membrane of the drum when you hit it, right? So vibrations can be caused by hitting. You know? Like let's say, so the example of vibration or oscillation is this. In one line. Okay. So is it vibration or it is oscillation? What is it?
Oscillation.
What's the difference?
So vibration is not in one line.
No. It's very fast. Why not in one line? Can't be in one line. Okay. Have you seen the needle of the shaving machine?
Ah.
That's why. That is vibration. Very fast. Okay. And this is oscillation, like a pendulum. Okay. So clock of the pendulum. But
Sir,
are you wearing any sound? So not every vibration will produce sound. So we'll come to it. Okay. So vibrating strings of musical instruments also are example of sound. And one of the instrument that you will use in lab is tuning fork. So vibrating tuning fork. Yes, you're asking something.
sir, fan is not oscillating.
No. It is periodic motion.
What's that?
So air is vibrating, right?
Yes.
We'll come to it. You'll understand, right? So and see, vibration is everywhere. Like here. Can you see the vibration? Can you hear the sound? So what is happening? This surface is vibrating going up and down. Okay. So likewise, there are bearing. Okay, there is friction. So there might be something at atomic level that you don't hear or that you don't see, but you can sense it. Okay. So it's little subtle, right? So like here also, it's oscillation or vibration. Is it not vibrating? Slow oscillation. But can you hear sound here? No. Can you see vibration there? No. But there are vibrations. Like when you touch any machine, you will feel the vibration. Like when car is going straight, you touch the body of the car. Everything is vibrating. Although car is moving straight. Okay. So vibrating tuning fork. Okay. So tuning fork is a steel rod which is bent in U shape. And a stem is connected at the bottom. Y-shaped object. This we call tuning fork. So basically, when you hit a tuning fork on some hard rubber pad, these prongs of the tuning fork will go. They will begin to go front and back. Okay. So this forward and backward. Front and back motion. It is also called to and fro. So it is referred to as to and fro motion, front and back motion, forward or backward. Okay. But what kind of motion? One time? No, repeated. Okay. So any motion which repeats itself after fixed interval of time is referred to as periodic motion. Okay. So vibrations are periodic. Back and forth. It's also called back and forth. Back and forth means front. But the common language is back and forth. Okay. So vibrations are periodic back and forth motion, back and forth, or to and fro motion. Of an object. Period you understand. What is the period? A fixed interval. Fixed time interval is called a period. Like what is your period, class period? 1 hour. Every interval is 1 hour for your class. Okay. So vibrations are periodic back and forth or to and fro motion of an object. So here what is oscillating? This cap of the camera. So this becomes an oscillator or a vibrator. The body which vibrates is the vibrator or oscillator. So in case of pendulum, the bob. The whole arrangement is called pendulum. But what is oscillating?
The pendulum.
The bob. Okay, the metallic bob. So is this clear? All right. Then it is also called as or oscillation. So sometimes it is referred to as oscillation. So both are same. So here the time period is more. It takes a lot of time to complete one oscillation. So what is one oscillation? Let's say this object begins to oscillate. So you can cause the oscillation in two ways. One is take it to one position. Now start the oscillation. So it started from one extreme, went to other extreme and came back. So in this case, the full oscillation is from one extreme to other extreme and back. This is one oscillation. So it is four part. It has crossed the mean or rest position. Rest position. And what is this? Extreme position. So one is A and B. So A and B are extreme position. O is the rest position. Okay. So there are four parts in any oscillation. Extreme to mean, mean to other extreme to mean, and then again B. Okay. So this is one period, one oscillation or one vibration. Okay. So how this vibration was created? When the motion was started from one extreme position. Okay. So here and here. The other way to start the oscillation is from the mean position when you strike it. Right? What happens? This is the rest position. Now you strike. So it goes to one extreme. When you strike, it goes to one extreme, then falls back. But it doesn't stop here. Due to inertia, it goes back. Okay. So in both cases, it has to cross the mean position. So how is one oscillation here in this case, in the second case? 1. Step 1. Step 2. Step 3. Step 4. So motion started in this direction. 1, 2, 3, 4. Now it is repeated. Now again. Now if you see the motion, after this it will repeat. You understand? So period is completed here. Now it is repeating again. So this is one oscillation. This is second oscillation. When the motion begins to repeat itself, then it is called one oscillation. So there are 4 parts in every oscillation. Clear? So if you look at the displacement, if you make a displacement time graph of this, what happens? Let's say you are representing the displacement. From mean position to extreme position is the displacement. Okay, and we are representing the displacement on the y-axis. So with time, the displacement is slowly increasing, maximum, and then it is slowly decreasing. Then it is increasing on the other side, and then it is. So this is one oscillation. Okay, so displacement time graph is like this. This you can call x, because right now it is oscillating on the x-axis. So x is represent, y is x-axis, horizontal displacement. So this full displacement, let us say, is a. And this side is minus. And we call this amplitude. During oscillation, the maximum displacement from the mean position is called amplitude. Okay. So these are the things. And time taken to complete one oscillation is called its time period. These 2 things you should remember. So every oscillation is characterized by its amplitude and time period. Then there is also something called as frequency. So number of such oscillations taking place in 1 second unit time is called frequency. So what is the frequency? Number of oscillations in unit time. So if t is the time for one oscillation, right? Then 1 by t will be the number of oscillations. Okay, so 1 by t per second. And this is also called as hertz. So the frequency of oscillation is reciprocal of the period, time period. All this we are going to do again, but since we are talking about sound, vibrating objects, so I thought let me cover what is vibration, what is oscillation. Okay, basically vibration and oscillations are same. Oscillations are vibrations. With large time period. Is this clear? That's it. So you may jot down all this. For these diagrams, etc., it will recall all the demonstrated energy. So the tuning fork is a specifically designed device. Okay. Whenever you hit a tuning fork, it will always create same sound. Right? Why same sound? Because the type of sound is characterized by frequency. Every vocal cord oscillates at different frequency. So when you speak, you have a unique frequency. He has another frequency. I have other frequency. So each sound is different from the other sound due to difference in their frequency. Okay. So every tuning fork also has a different. So like if I hit this, it sounds different. If I hit the door, it's sounding different. Because both the sounds are happening at different frequency. Is that clear? What determines the frequency? The geometry, the shape and size. So every vocal cord also will be of different shape and size. Okay, so that's how it is. Is that clear? So I was talking about tuning fork. So every tuning fork is designed to vibrate at a particular frequency. Therefore, every time you vibrate it, it will produce the same sound. And that frequency is printed on the tuning fork. Okay? So you may have two different tuning fork and you may find different frequencies marked on it. One is say 100 hertz, the other maybe 200 hertz, like that. What about others? Are they
All of them are exams.
oh, or some people may not come.
So most of them are from that not going to get their exams are going.
Okay, so we'll go slowly. I now remember Azam had asked. Azam is not in North Point, right?
Three people from total are not from North Point. Azam is from Goregas.
His exams are also going.
I don't. He's just finished, right? He showed the paper.
I don't know why he's not come. Then maybe he will. Now what he will come? It's already late. So we heard what is sound. I mean, we learned what is sound and how it is produced. Now we will learn something else. Propagation of sound. Done right here. Although here. So are you able to hear? I'm also able to hear. So sound was created here. The source of sound is this, but the listeners are at different position. So sound is detected at position A, then position B, and position C. So sound must have reached you. This traveling of sound is called propagation. Okay, so we now need to understand how sound has reached you. Okay, this is what we want to understand. So basically, what has happened is, so where is the ear? Here, the sound has reached you through air, right? So sound requires medium for propagation. Sound propagates through a medium. It cannot propagate without medium. It cannot propagate in vacuum. So in space, if I'm trying to speak to you, you will not be able to listen to me. Okay. The sound propagates through a medium. The medium could be solid, liquid, or gas. Gas as in air. So, like when I'm hitting this table, if you place your ear on the desk, you'll hear the sound through the desk also. Through here, anyways, we are hearing it. even inside liquid, okay, let's say you're swimming inside, you will be able to hear sound. Okay, let's say if you're inside, some creature or some ship is running or engine is running, you will be able to hear while you're still underwater. Okay, so sound propagates through all three media. Okay. How it propagates, we'll see. So speed of sound is maximum in solids. Then in liquids. Then in gas. The speed of sound is least in gas. Okay. So solids. Yes. Okay. But most familiar sound medium for us is gas. The speed of sound in air is it's about 336 meter per second. Okay, that's the speed of sound. You will also see or 334 meter per second. This is at normal temperature and pressure. Normal temperature, that is room temperature. Roughly 25 degrees Celsius. Say at room temperature. Okay. At STP, standard temperature, that is at 0 degrees Celsius, the speed is little less. Okay. So the speed of sound increases with temperature and it reduces with density. If the medium is more dense, right? So speed of sound depends on, I'll just write down. The speed of sound depends on elasticity, density, and temperature of the medium. Okay. So the formula for speed of sound is this. You will learn about this formula in higher standards. It is inversely proportional to density and it is directly proportional to the elasticity. Of course, square root of that. Okay. Which means if the medium is more elastic, the speed will be more. What is the meaning of elasticity?
The ability to which a medium can stretch.
Yeah, that's like layman's view. Like if you stretch a rubber, right? So it is stretched, and then when you leave it, it regains its original shape. So regaining the original shape when the external forces are removed. Okay? If any body regains its original shape when the external force on it is removed, then it is a better elastic body. That means it is flexible. So through the flexible medium, the speed of sound will be more. Okay? And if the medium is dense, thick, then its speed will be hampered. Because dense it will resist. Okay. So for that, let us understand how the propagation of sound takes place. So rho is where E is elasticity. E is elasticity. And density is rho. It's called rho. RH. This is how it is pronounced. So Greek letter rho. It represents density. Okay, I will tell you density and elasticity. So formula not in scope right now, but to explain, I thought I'll just put it for you. No, it is. You're in ICSE, right?
Yeah.
We have, right? In CBSE, it is not. Okay. So now, Let's understand propagation of sound. So imagine you have a tuning fork, right, which is not vibrating, and the listener is somewhere here. Okay. So what is between the listener and the tuning fork? Air particles. And they are uniformly distributed. When it is not vibrating, the air molecules are uniformly distributed. Now, when the tuning fork is set into vibration, so what will happen to the prong of the tuning fork? It will begin to make back and forth motion, right? That means it will begin to go forward and backward. So the air molecules which are near the tuning fork, what happened? Air molecules which are near the tuning fork will be compressed, right? So it will move in this direction. And then it will disturb the next one. Okay? Tuning fork vibrating will disturb the air molecules closest to it. It's like, let's say there is a line and 4-5 students are standing here. So I push the student near me. So then what happens? He will fall on the next one. The next one will fall on the next one. So what is traveling? Is the student traveling? Is the student traveling? He's just falling. Let's say I place bottles like this, and I just make one bottle fall on the next bottle. So is this bottle traveling? No. What is traveling? The disturbance. Each bottle begins to fall now. So what has traveled from the first bottle to the last bottle? Just the push. What has traveled? Push or the disturbance. So this is what happens during propagation of sound. The air molecule has pushed the next one. This has pushed the next one. And finally, the air molecule inside the ear, okay, disturbs the eardrum. Okay. Now, this tuning fork just does not lean forward; it also comes back. So when it comes back, then this molecule begins to recede back. Okay. So basically, what happens is due to this vibrating tuning fork, even this air molecule vibrates front and back, like that. And after a while, this also does the same thing. Okay. And during this, what propagates is the disturbance. Now the disturbance is sound wave. Understood? The push which is traveling, that is sound wave. Okay. So this motion is nothing but energy. So sound energy, right? So when we spoke, it disturbed the molecule. It sent the molecules in motion. So initially it had zero kinetic energy. Now it has kinetic energy. It goes ahead and collides with the next one. So that now gains kinetic and this goes back. Okay. And by the time it goes back, it comes forward again. Right? And this continues. As long as this is like I have to continuously speak so that you are able to hear me continuously. When I stop, even the air molecules begin to slow down. They also stop. So during this, what is happening is these air molecules are coming closer. So I'll now represent it with the help of a line. Some regions it will come closer, and when it goes back, then it will be spread apart. Okay. So there will be a region where the air molecules will spread apart, and sometimes they will come closer. So like this, different regions are created. So the regions where the air molecules come together is called compression. And this is called rarefaction. Compression, rarefaction, compression. So this is how the sound wave travels by forming a series of compression and rarefaction. So C stands for compression. R stands for rarefaction. Okay. So what is happening during compression and rarefaction? The disturbance or the sound wave. This propagation of disturbance from molecule to molecule. Air molecule is not traveling. What is traveling is the disturbance. This fast ahead. That disturbance is called sound wave. This is called sound. So finally, when the air turns begins to vibrate, right? So that creates that vibration is created into electrical energy that is transferred to the brain through auditory nerve, and then the brain senses that as a sound. Is that clear? This is the full mechanism of propagation of sound. Now, I'll just give you a video animation which will just show you the same thing what I just explained. And we'll stop here today because others will miss otherwise. Oh, we already have a YouTube video. Propagation of sound. So this is a nice animation.
In our previous video, we studied that sound needs a medium for propagation. That is, it requires some medium to travel from one place to another. But how does it really travel through the medium? What happens to the particles of the medium? Let us find out. We now know that sound is produced by vibration. When the object is vibrating, it sets the particles of the medium around into vibration. In the process, the nearest particles to the source gets displaced from their mean or equilibrium position. These don't collide with the particles adjacent to them. The adjacent particles then also get displaced from their mean position. They in turn do the same to their neighboring particles. This process continues in the medium till the sound reaches our ear. We see that we create some disturbance flowing through the medium. That's the way that sound travels through the medium. We see that particles of the medium are not traveling from the source to the human ear. It is the disturbance produced by a source which is traveling in the medium. Particles are merely oscillating from their mean position.
So no particle is traveling. They are only oscillating around their main position. And if you focus on this compression, and then you focus on this compression, you'll see that the compression is going ahead. If you focus on rarefaction, you will also see that the rarefaction is going ahead. Okay. So what is traveling is either compression or rarefaction. You can focus on any. You see.
Disturbance by the vibrating object in the medium is what we call a sound wave.
Rarefaction.
But what does this disturbance look like? Let us study this with the help of a tuning fork. Here we take air as a medium of propagation. Here we have a tuning fork made up of steel. This shows the initial condition of the air particles of the medium when the tuning fork is in its original position, that is, when tuning fork is not vibrating. When we strike its crown on a rubber band, we start hearing a sound. How does the sound travel through the medium? The two prongs of tuning fork are vibrating. Let us concentrate on motion of one of the prongs first. Then the one on the right. When it's away from its main position, it pushes and compresses the air particles around it. This creates a high pressure region, also called compression.
So high pressure, high density.
Travels in the medium as a disturbance. Here the density is high. That is, the particles are very close to each other. When the prong comes towards its mean position, the pressure on the right decreases and keeps on decreasing further as the prong continues its motion towards left. This creates a low pressure region
also called as rarefaction. We see that at this point, the compression in the form of disturbance has reached this region. This rarefaction also travels in the medium as a disturbance. Here the density of particles is less. That is, the particles are far away from each other. As it continues to vibrate, we get a series of these compression and rarefactions. This continuous sequence of compression and rarefactions is what we call sound waves. Yes, the sound waves travel in the form of compression and rarefaction.
A series of that, not just one. Okay. So I think for today, I think we'll stop here. And we have some 2-3 more minutes. So what you have seen is this disturbance travel with some speed, and that is speed of sound. And the particles of the mediums are oscillating like this, parallel. How is the oscillation of the particle? Parallel. So this kind of propagation of disturbance, when the oscillation is parallel to the motion of the wave, is called longitudinal wave. Okay. So sound is the example of sound wave. There are different types of wave. Yes. So first of all, it requires a medium. So it is mechanical wave. Wave of longitudinal type. Okay. Mechanical wave because it requires a medium. Any wave that requires a medium for propagation is mechanical wave. And when the particles of the medium oscillate parallel to the direction of the wave propagation, then it is called longitudinal. Okay. So sound wave is example of mechanical wave of longitudinal type. So do we have any other type of wave? Yes. Transverse wave. So like water waves. How are water waves? Like water wave travel, water oscillate, or water molecule oscillate up and down. Like there is a still water, okay, near a pond. Now you drop a stone. So what do you observe? You observe that circular ripples will form and it will spread out. So what is spreading out is disturbance. Water is not flowing. It is giving you the impression that water is flowing outside. No. Water is only oscillating up and down around its main position. But when one water is going up and down, it disturbs, passes the disturbance on the adjacent water molecule. So what is transferred is the, so now the next water molecule is also beginning to go up and down, but it happens in different times. And you get an impression that the water is flowing out. It's not water. What is flowing out is disturbance, which is wave, water wave. So the other type of disturbance is transverse wave. तो लॉन्जिट्यूडनल में क्या होता है ऐसा होता है so mechanical transverse wave such as water waves on the free surface of water. What is free surface of the water? The top surface that you see. There are deeper layer also, like on inside. There also there is water wave, but that is not transverse. Transverse is only the free surface. Surface is what you see up and down, right? So how is the wave here? The molecules oscillate up and down, and the disturbance travels like this. So there is a perpendicular. In this case, it is parallel. Particles oscillate parallel to the direction of wave propagation. Here, the Water molecules oscillate perpendicular. Then it is transverse. That's why it is transverse. Okay, it's not parallel, it is trans. So this is example of transverse. Now, light wave is also having transverse nature, but it does not require medium. It can travel through space also.
So how light is transverse?
So light can travel in space. That means there is no particle to oscillate, right? So you study in higher standard that every light wave, when it is coming towards you, so let's say light is coming towards you. So it has electric and magnetic field components which oscillate perpendicular. So it is the electric field and the magnetic field. That's why it is transverse. And electric and magnetic field is also energy. And when the electric and magnetic field change, they create each other. That's how they don't require medium. Here the energy transfer is taking place through the particles of the matrix. Here the energy is recreating itself. Electrical energy creates magnetic energy, magnetic energy creates electrical, and that's how they propagate. It's an advanced concept. So right now you just understand that light is also a transverse wave of, but it is non-mechanical. It's called electromagnetic wave. Okay, that's a separate category. Light wave is transverse wave of electromagnetic type. But sound and water wave are mechanical waves because they both require medium. Okay, we'll discuss more in the next. Do you have any other class today? Which one?
Second. Okay. Oh shit. Ah.